So in the last lecture, you had the chance to learn a little bit about the components that contributed to the resting membrane potential. In this lecture, we're going to be talking about what happens to that stored energy, that potential energy at the membrane, once it's given the opportunity to be released. So that is what the nerve impulse is, and we call it the action potential. So in the 1950s, Hodgkin and Huxley, so Hodgkin's shown here on the top right and Huxley's on the bottom here, both of them worked together to figure out how neurons carried the electrical impulse. At that point, there was no clue as to what the means by which neurons carried the information within itself. And they used the giant axon of a squid. For a while there, I thought it was a giant squid, which I know lives in the depths of the ocean, but in fact, squids have a very big axon that can be manipulated, dissected and manipulated in a petri dish, and so they use the giant axon of the squid as a model to better understand the ways in which the nerve impulse of the action potential is generated. And this was essentially their setup here on the left. So they took the giant axon and put it in a petri dish filled with fluid that had all of the necessary components to generate an electrical impulse. They had two recording electrodes, one that was inserted into the axon and one that was kind of hanging out on the outside. Because remember, the resting membrane potential is a relative measure. The inside is slightly more negative, but only in comparison to what's on the outside. And they hooked up these electrodes to an oscilloscope, which allowed them to view the changes in voltage over time, right? So it recorded millivolts or voltage, and it did it in very quick timing period at the level of the millisecond. So in this way, they could observe what the electrical activity was in an axon. So when they recorded it, this is what they saw: a total flat line at the negative 70 millivolt mark. Didn't change, nothing happened to it. This was what it was, and this was the resting membrane potential. So remember, at rest, nothing's happening. The neuron isn't doing anything. It's just maintaining the negative 70 millivolt difference across its membrane. That's all it's doing. So they had the brilliant idea of attaching a stimulating electrode to the axon and sending current into the axon to see how it would change. So current typically are positive ions, and so they wanted to see what would happen if we sent positive ions down the stimulating electrode, and how would that change the activity that we observe in the recording electrodes. So when they applied the first stimulating electrode, the first stimulation, not surprisingly, they saw a slight increase, right? Slight increase in the membrane potential. So membrane potential, I'm just going to refer to the change in voltage that happens across the membrane. And I can't seem to get my pen back. Here it is. Then they applied a greater stimulation and found that the membrane potential increased again. It became slightly more positive relative to the stimulation they added to the membrane. So that wasn't surprising. But when they increased the current a third time, they expected to see this, but in fact what they saw was this. This is the action potential. And it turned out enough current was sent through that stimulating electrode to reach what is known as the threshold of excitation, which is required to generate the action potential. And the threshold of excitation, on average, for neurons is negative 62 millivolts. It's a more positive value than the resting membrane potential. So let's take a look and see what's going on. What's contributing to the action potential is that second category of ion channels that we talked about in the last lecture, and that's voltage-gated ion channels. So again, these ion channels are selective. They only allow their specific ions through them, but they are gated by voltage, which means that unless the voltage changes to their particular preference value, the ion channel will remain closed. So ion channels that are voltage gated tend to be sensitive to changes in voltage. These are voltage gated ion channels. The axon has voltage gated ion channels for sodium and potassium. The threshold that opens these channels up is different for each type of ion channel. For sodium, the threshold that opens the channels up is the threshold of excitation, which generates the action potential. For potassium, the voltage necessary to open it is a value even more positive, one that's closer to 0. So, voltage-gated ion channels have particular characteristics. They demonstrate a voltage-gated opening. They demonstrate a time-dependent closing, so over time they close. And they demonstrate what's known as refractory period, a refractory period where no matter how much stimulation you apply, you won't be able to open it. The function of this refractory period is to ensure that the action potential, once it's started, moves down the same direction, down the length of the axon as opposed to back up it. The function of the refractory period is to ensure that the axon is unidirectional and moves down the length of the axon rather than becoming bidirectional and moving in both ways. So let me just show you the ways in which the refractory period serves its purpose. So at rest, all of these voltage-gated sodium channels that I drew are closed. When the threshold of excitation is met, you're going to have this first voltage-gated sodium channel open. Sodium is a positive ion, right? There's more sodium outside the cell. Sodium is going to rush into the cell and make the adjacent, on both sides, adjacent membrane more positive. This is going to cause the next voltage-gated sodium channel to open. Sodium is going to rush in again, but rather than sodium opening this first ion channel again, it can't because it's in refractory. So instead, what happens is the sodium ends up just opening the adjacent ion channel, and in this manner, the action potential moves down the length of the axon in one direction, and it doesn't end up traveling in both directions, which isn't supposed to happen. So the function of these ions entering refractory period shortly after they open is to prevent the movement of the action potential in both directions. It forces the action potential down the length of the axon, in one direction only. Now that we've talked about the ways in which refractory periods contribute to the movement of the action potential down the axon in one direction, let's talk about what's actually happening during an action potential. So you know this setup already, right? So sodium and chloride are present at higher concentrations outside the cell, whereas potassium is present at a higher concentration inside the cell. And the inside of the cell compared to the outside is slightly more negative. Once the threshold of excitation is met, these voltage-gated sodium channels open. And remember, the force of electrostatic pressure and diffusion are both desperately pushing sodium into the cell. So this causes gobs of sodium to enter the cell down its both electrical and concentration gradient. So much sodium enters the cell that the inside now actually becomes positive relative to the outside. This causes voltage-gated potassium channels to open. Voltage-gated potassium channels have a threshold of excitation that's slightly higher than that of sodium. So the value of the membrane potential actually needs to reach closer to 0 in order for them to open. But once they open, now remember, the inside of the neuron used to be negative, but now it's positive. So potassium is actually going to go down both its concentration and electrical gradient to the outside of the cell to get away from those positive charges and to where there's less of it. The voltage-gated sodium channels demonstrate a time-dependent closing, so they close after about 1 millisecond, and potassium continues to leave the cell. continues to leave the cell, making the inside once again more negative compared to the outside. Because when positive ions leave the cell, they're going to leave behind negative charges. So let's take a look at what's happening to the inside and outside of the cell on that graph, right? And so we talked about the movement of these ions across the membrane during an action potential. Let's apply it to that graph of the action potential I showed you earlier. So we have a resting membrane potential here represented by R and P. And here's the general shape of the action potential. So at rest, a neuron is at negative 70 millivolts. When the threshold of excitation is reached, which is negative 62 millivolts, we are going to generate the action potential. But at the start of, or at rest, the inside, shown here, is more negative compared to the outside. So when the threshold of excitation is reached, voltage-gated sodium channels open. Because the forces acting on sodium are so great that given any opportunity to enter the cell, gobs of sodium rush into the cell. Sodium, remember, is a positive ion. So when it enters the cell, it makes the inside of the cell, which is represented by this change in graph, it makes the inside of the cell more positive, right? So now the inside of the cell becomes positive. It reaches the threshold for voltage-gated potassium channels, which open. Potassium starts leaving the cell, but the problem is so much sodium is entering the cell that potassium leaving can't counteract the positive effects of sodium entering the cell. So sodium continues to drive the membrane potential to be more positive until the voltage-gated sodium channels close. Remember, they demonstrate a time-dependent closing and close after 1 millisecond. Now the sodium channels are closed, nothing is entering the cell, but potassium continues to leave the cell. Potassium is also a cation, it's also positive, so it's going to make the inside of the cell more and more negative as it continues to leave. So the inside of the cell slowly becomes more negative compared to the outside. After some time, potassium channels gradually close, and the cell returns back to its resting membrane potential value. What's absolutely incredible to me is that all of this happens in 2 milliseconds. I didn't say 2 seconds, I said 2 milliseconds. That is lightning fast. Like, you couldn't even blink 2 milliseconds. That's how fast it is. It's like a blip. You know, it's almost like you don't see something happen when it happens. What I love about this, or I love pointing out to students, is that this is happening all the time, everywhere in your nervous system, and continuously across all axons in your brain, in your spinal cord, in your body. What allows you to do what you can do, which is listen to me, watch this lecture, listen to me talk and explain it. All of it is the result of these action potentials that are happening, all over neurons in your nervous system. And it happens lightning fast. This is an image from your textbook kind of illustrating the same thing that we just talked about, but in one figure. So here they're using the threshold of excitation as negative 55 millivolts, but it's pretty much the same. So once the threshold of excitation is reached, an action potential is generated, and these numbers represent the different events that happen that we talked about. So at 1, which is baseline at rest, voltage-gated sodium and potassium channels are closed. There's more sodium outside the cell, more potassium inside the cell. But when the threshold of excitation is reached, voltage-gated sodium channels open, sodium rushes in, making the inside more positive. Around 0 millivolts, voltage-gated potassium channels open, but the amount of sodium entering the cell cannot be counteracted by the minimal potassium leaving the cell, so the membrane potential continues to rise until the voltage-gated channels close and enter refractory period, preventing sodium from entering the cell. At this point, potassium continues to leave the cell, making the inside more negative. And right around the dip past the resting membrane potential, the potassium channels close and the system resets. Okay, so this is just a different way of looking at exactly what we talked about over the last couple of slides. So this is a situation we're left with at the end of the action potential. We have tons of sodium inside the cell and tons of potassium outside the cell, even though the inside of the cell is negative relative to the outside. But that's not how it's supposed to be. At rest, sodium is supposed to be present at a higher concentration outside the cell and potassium inside the cell. So what happens? How do the ions get redistributed back to where they were before the action potential started, which is potassium inside the cell and sodium outside the cell? If you guessed sodium-potassium pump, you are correct. The sodium-potassium pump helps redistribute these ions to where they need to go. So 3 sodium gets pumped out for every 2 potassium that gets pumped in, and the system resets itself for another action potential. And it's hard to imagine how quickly all this is happening, but it is incredibly fast. When you think about the number of action potentials your neuron, a single neuron in your body can generate, it is super fast, right? It's back to back to back action potentials. About every 1 second, an action potential can occur. I'm sorry, about 1 millisecond, an action potential can occur. And so this turnover in ions getting redistributed back to where they need to go happens super fast. It returns back to its resting membrane potential. So yeah, I failed on that animation right there, but hopefully you get the picture. One thing that you need to be aware of is that action potential generation in myelinated axons is very different from action potentials generated in unmyelinated axons. So what we talked about earlier when we discussed the refractory period, where adjacent voltage-gated sodium channels open, kind of like a domino effect down the length of the axon, that does not happen in myelinated axons. In fact, myelinated axons only have voltage-gated sodium channels at the nodes of Ranvier. Underneath the myelin, there are no voltage-gated sodium channels at all. So what myelinated axons demonstrate is something called saltatory conduction. It's just a fancy word, but really all it's saying is because voltage-gated sodium channels are only present in the nodes of Ranvier, sodium enters the cell through these nodes of Ranvier, or at the site of the nodes of Ranvier, and because there's no opportunity for sodium to leak out of any possible channels that are open, because there are none that are expressed underneath the myelin sheath, sodium is driven down to the next node, which reaches threshold of excitation, causing the action potential to be generated here and then driven down to the next node. In this way, the action potential is much quicker in moving down the length of the axon. It's propagated a lot faster than it is in an unmyelinated axon, where it's like ion channel opens, another ion channel opens, another ion channel opens, which is very slow in comparison to the saltatory conduction that occurs in myelinated axons. There are a couple of laws that the action potential follows. The first one is called all or none. So the all or none law essentially gets at the fact that an action potential either occurs or it doesn't. Either the conditions to have an action potential are met, that is, the threshold of excitation is reached, or it isn't. If it's met, an action potential occurs. If it's not met, an action potential does not occur. What's really interesting is I love the analogy that I read once in a textbook for the all or none law. It's kind of like a toilet flush. You can't flush the toilet a little bit. You reach that kind of breaking point where you've pushed the lever down far enough that all of it is going to be released, all of that water is going to be released, and there's no stopping it. And the action potential all or none law is very similar to that. So once the threshold is met, once that lever is pressed past a certain point, there's no going back, an action potential will occur, or all of the water from the toilet container will be released. The other aspect of the all or none law is the is the intensity of the action potential. It says that the size and intensity of the action potential stays constant. So regardless of where down the axon you measure an action potential, it will remain the same size and same intensity. You can't have a big action potential, you can't have a small action potential. It is what it is, kind of like Goldilocks. It is what it is. The size and intensity of action potential stays constant as it travels down the length of the axon. The second law is the rate law. When you think about it, our behaviors are not very black and white. We aren't like all or nothing. We don't, pick up an egg with the same intensity that we pick up a textbook. They're totally different things. So how does the nervous system use action potentials, which are all or nothing, and translate it into something with variation, which is what most of our behaviors are? Has to do with the rate or frequency of action potentials. So the rate of action potentials or axon firing is what permits graded behavior or action. So the frequency of action potentials or APs determine the strength or intensity of behavior. And so here are some examples of current or stimulus injected in the axon. This particular stimulus doesn't even reach the threshold of excitation, so it doesn't generate any action potentials, but this one does, and it's a little bit greater than the one before, so you have a certain number of action potentials that are expressed or that occur in this span of time. But if you generate, or if you increase the current even further, you're not going to generate a bigger action potential, but what you are going to do is you're going to generate more action potentials. So the frequency or rate of action potential increases relative to the stimulus or intensity of the stimulus. So that's it for the action potential lecture. Let's quickly summarize what we've covered here because it's actually quite a bit of information. So the action potential is generated when the threshold of excitation is met, which causes voltage-gated sodium channels to open. The influx of sodium causes the inside of the neuron to become more positive, ultimately opening voltage-gated potassium channels. The reversal of charge across the membrane is essentially the action potential that travels down the length of the axons, and following an action potential at a particular location on the axon, the ions get redistributed by the sodium-potassium pump. When action potentials travel down myelinated axons, they end up using a phenomenon known as saltatory conduction, which increases the speed of travel. So you only have action potentials happening at the nodes of Ranvier, not underneath the myelin. So the speed of conduction of the action potential is much greater in myelinated axons than it is in unmyelinated axons. Action potentials also follow the all or none law, remember toilet flush, and the rate law, which is intensity of stimulus is related to the rate or frequency of action potential. So that's it for this lecture. Don't forget to submit your reflection.